Hello, everybody. As you have already heard, I am Claudia De Torre, a PhD student at University College London. As I said in my previous speech video, today I'm going to present you my work accepted at IPCAI 2022 on learning intraoperative organ manipulation with context-based reinforcement learning. But this time, I'm going to provide you a little bit more details. Again, pretty similar overview of the presentation. I will first define the clinical motivation behind studying intraoperative organ manipulation procedure, to then provide some more details on the setup of the PAF rail. I will then explain how the problem can be formalized, followed by a more detailed example of the pick and place task. We'll then follow the methods, more detailed experiments, and results section that will walk you through how to use reinforcement learning for solving these tasks. And we'll then end the presentation with some conclusions and discussions. As you have already seen before in a sample of this video, we have an experienced surgeon that is executing the repositioning of a porcine kidney. As we can see, she's using the tool shaft to control the position of the organ and uses the wall of the lab box to support when lifting the organ. This is normally a very challenging procedure and it can be prone to multiple slippages, as you can see also happening in this video right now. In this work, we propose a solution, the use of the pneumatic attachable flexible rail that can be used as a suction handle placed over the organ to allow surgeons to simply manipulate them using a single robotic tool. As we can see, the suction force allows to lift the organ without the need of using any support. This is an overview on how the rail works and how it can be set up. We have a suction pump that is used to generate the suction force inside the vacuum chamber. The pressure line is then inserted along with the rail inside the trocar and deployed over the organ. Here on the left, we can see a better close-up. The rail used in this experiment has a slightly different design from the one in the picture, and it allows to have multiple grasping sites along its whole length, as highlighted from the colorful markers. With a better understanding of the clinical context and of the PAF rail, this work aims to automatize the pick and place of the PAF rail to support surgeon during long and demanding surgical procedure. To achieve this goal, we rely on the use of a deep reinforcement learning agent to learn how to execute the task. We can now introduce RLMan as a reinforcement learning framework that relies on a simulation environment compatible with the state-of-the-art library for reinforcement learning and also with the Da Vinci Research Kit. In RLMan, different manipulation tasks can be trained in different environments. Before getting more into details about the methods, it's important to specify that in order to be able to use reinforcement learning to solve these tasks, the entire problem needs to be defined as a Markov decision process that can be formalized as an agent that is able to act over an environment, and it gets as feedback the state information and the reward. Let's have a closer look to the pick and place task, for example. As we said, we have an agent and the environment. The state is characterized by the position information of all the objects in the workspace. Additionally, the task is defined as goal-oriented in order to be able to use Insight Experience Replay algorithm. Therefore, the state information are augmented, adding the desired goal and the achieved one. And we have the action as described before. And we can see how the aim of the task is to grasp the rail and retrieve it over the circular target. For the reward, we define it as sparse, and particularly it gets value -1 when the distance d between the robot and the goal is greater than the threshold delta, defined arbitrarily as 3 mm, or 0 when lower. In order to train the reinforcement learning agent to solve the desired tasks, we tested two different approaches. One, relying on high-dimensional state representation, where the agent uses camera frame to gather information about the environment. In the adopted algorithm, this frame are used as input for the actor network that select the best discrete action to take in order to maximize the cumulative reward. Given the complexity of the problem, the action space has been discretized, defining a set of 7 possible actions. For the low-dimensional state, we use the Cartesian position of all the objects in the workspace. I use them as input of the actor critic network that in the same fashion selects the best action to take in order to maximize the reward. Additionally, we also augmented the state representation with some contextual variables that are used to investigate how they can affect the overall task execution and the capability of the agent to generalize over the task. Specifically, we introduced the following variables derived from each task, such as the grasping side as the possible grasping position of the rail, the end effector initial position, the rail initial position and orientation, and the location of the circular target. We also introduce obstacles to simulate abdominal area that we want to avoid when executing the task, and we randomize their dimension at each reset, sampling from a predefined range explained in the figure. Overall, we ran 2 sets of experiments. The first one, training different manipulation skills and comparing the results with the benchmark found in the literature. Specifically, we defined 4 different subtasks, such as reaching, picking, retrieving, and pick and place. And we compared the results obtained in RLMan with similar tasks trained in Surroll. It has been possible to compare the following results because despite the 2 frameworks relies on different engines to power the simulation environments, the selected tasks present the same Markov decision process definition. Therefore, the results can be compared. The compared tasks have been trained with the same algorithm too. In the second set of experiment, we analyzed the importance of the environment variable described before and different definition of training volumes. Here are the interesting results obtained for the 4 different subtasks. Let's have a closer look. Starting from the reaching task. In this case, the agent has to learn how to move the robot to reach a desired target. As we can see from the graph, the agent is able to correctly learn the task because the success rate converges very close to 1. For the Surroll framework, we are going to notice how normally success rate for each task during training will present lower values compared to the RLMan. This is probably due to the different definition of noise applied during training. For the picking, the aim of the task is to correctly pick the target object. Also in this case, we can see how for both environment and agents seems to be able to learn how to execute the task correctly. For the retrieving task, we are comparing the retrieving of the rail over the kidney for RLMan and the gauze retrieving for Surroll. In both cases, the tasks seems to converge to a success rate between 80 and 95%. And as last task, we analyzed the pick and place of the rail for RLMan and of a surgical needle for Surroll. Given the complexity of the task and the delay reward based on the success of the intermediate step of picking the object, these tasks reach lower success rate compared to the previous one, but still above 50 and 60% of the success rate. Here is a sample of the trained agents and how they are able to execute the aforementioned tasks. Now, moving on some details for the reaching task using high-dimensional state information. For this experiment, we decide to adopt algorithm, which gives some high-dimensional input, are able to determine the best discrete action to take. We slightly modified the environment, adding the endoscopic camera and the vision sensor. As said, the state information is represented by the frame coming from the camera that have been pre-processed, downsampling them in order to speed up the training. For the reward function, we adopted a dense reward in order to guide the learning with more information. And for the action, we define a set of 7 possible actions that the agent can select from. Stay still, or moving forward or backward in the 3 orthogonal directions, with a step size of maximum 3 millimeters. Here are the results obtained during training. In red, we have the agent trained to solve the same task by using low-dimensional state information. While next to it, we have the results obtained from 2 different algorithms using high-dimensional state definition. On the top corner, we can see how both using DQN and PPO, the agent are eventually able to learn how to execute the task. Here in the box plot, we are displayed the average error distance measured at the end of the task compared to the distance between the robot initial position and the target. As we can see, the final error increases with the increase of the initial distance. This is probably due to the fact that the agent will have to explore more before actually getting to hit the target. Now, moving on the results obtained when analyzing the different environment variables. As described before, we define 5 environment variables. For each experiment, we only randomize part of them. Starting from the first one, where only the grasping site is randomized. For each of the experiments, we consider 2 different training and testing volume configuration. In one case, where both the volume are the same size, and in the second case, we sample 1/4 of the volume only for testing. In the second experiment, we also randomized the rail position and then randomized the rail orientation. While in the fourth, we kept fixed the rail orientation and randomized the target instead. The orientation of the rail represents one of the most critical environment variables, as we can see. We then add the randomization of the robot initial position to then conclude with all the variables randomized. As we can see, in this very last case, performances become quite worse. This is due to the fact that in this case, oftentimes the environment happens to be in an extreme configuration that cannot be solved during the duration of an episode, as we can see from this image where the robot, the rail, and the target are all in a far relative configuration. Let's conclude now with results obtained from training the pick and place task with obstacle. In this task, we had 3 obstacles whose position and dimension gets randomized inside the workspace volume. As we can see from the success rate during training and testing, the agent seems to start learning how to execute the task, despite the final value are still below 30%. Here on the right, we display 2 success samples trajectory of the task. These preliminary results are definitely encouraging for further research in understanding how to push the agent to learn in these hostile environment conditions. And finally, to conclude, in this work, we introduced the RLMN framework for training manipulation skills compatible with the DVRK that allows to work in both low and high dimensional state representation. We analyzed 4 main tasks comparing results with benchmark. We reported promising results on agent be able to execute a simple task using information coming from a vision sensor. We examined the importance of contextual variable in order to be able to generalize over unseen environment. We reported preliminary results on agent trained in an hostile environment where there are obstacles to be avoided when executing the task. And in future work, we aim to translate all the experiments from simulation to the real robot. Thank you very much for your attention and for selecting this work for extended presentation. Please don't hesitate to scan the code and read the full version of the paper. Thank you.